So I'm going to come in and I'm going to start lecturing. And one of the things that you want to sort of like pay attention here is that what you're going to find is that my whole job here is essentially not to help you with every detail, but essentially to be sort of like, how do I say this? Is to help you with the hard things. Now, I know that you're coming off of Physics 4B, or you've taken Physics 4B in the past, and you're going to see that the circuits that you see in this course is considerably more complicated than what you saw in Physics 4B. I think that's pretty safe to say. And I figured we should start right away. So let's do this here. And another thing that I should say here is that you should treat this class with respect. I think that you probably have heard about the reputation of this course, and it could be pretty stout. So if you're right on top of it, my experience is that at the end of the semester, I have almost 100% pass rate. The average is typically in the mid 80s, and I give a shitload of A's. And a lot of people are going like, I can't believe that there's that many A's. And I can, because my experience with circuit students is that they're extremely good. But it's because you're probably scared the shit out of you as we go through the semester. That's probably the real reason. Okay, here we go. We're going to start with chapter 1. So chapter 1 is called Circuit Variables and Elements. And I can't really say that this is a review. Some of it's going to be a review, but I think a lot of it is going to be a lot about language and sort of like getting a handle on things. And what you're going to see here is that there's really two parts to this thing. There's a piece called variables, and you're going to see that with variables, we're going to deal with the real standard things, right? We'll redefine briefly, what do I mean by current? What do I mean by voltage? But a really big thing on circuits, believe it or not, is power. Power is a very, very important parameter in circuits here. And what you're going to find here is that power really is broken down into two pieces. There are elements that are called passive, that absorb energy, and there are elements that are called active, and they supply energy to the circuit. So we really got to nail that, and you're going to see that in the future. It's a common question that I'm going to ask: is the circuit active or passive? Or excuse me, is the element active or passive? So it's a big deal when we start to look at this thing here. Okay, so then what we want to do here is that then we're going to talk about elements. And I'll briefly tell you that the kind of elements that we deal with are only linear. And what I mean by linear is that it means that they're low voltage circuits. And what you're going to find here is that the elements that we really want to pay attention to is, of course, one of the easier ones, the resistors. And we need to talk about sources. And what you'll find here is that the kinds of sources that you're most familiar with are voltage sources. But there's another kind of source that's known as a current source. So I have to go in there and tell you, what do I mean by a voltage source? What do I mean by a current source? But there's another breakdown. It turns out that there's two kinds of sources. There's an independent source, and then there's a second kind of source, which is known as a dependent source. And you'll see that this independent and dependent, they get they can get fairly involved. And that's where we really want to go here. So if you want to ask yourself, what are you supposed to get out of this chapter? This is what you're supposed to get out of these elements right here. Okay, so let's go talk about variables. So the basic answer that almost every question about a circuit is that you want to calculate either the current, the voltage, or the power. But the power is a function of current and voltage. And what we find here is that when we calculate the current and the voltage, it also depends on the property of the element. In other words, is it a resistor, a capacitor, inductor, or whatever it is? So when I look at the type of circuit and I want to calculate, so the type of circuit will dictate, no, there's a T in here, right? Dictate, will dictate the method of approach. To solving for current and voltage. And what you're going to find here is that this approach depends on two things. So the first thing that it has to depend on is it depends on the types of elements. And the standard element that you saw, so you talked about resistors and sources in physics 4B here, and it turns out that these guys are linear. And because they're linear, you can use systems of equations to actually solve for these things. And that's exactly what we'll do. However, if you start talking about like capacitors and inductors, these guys are nonlinear. And because they're nonlinear, they require differential equations. Or unless you do a transformation into the complex plane, and then you start doing some type of phasor calculation. So the type of element really starts to tell you your method of approach. The other thing that it depends on, as you're going to find here, is that it depends on the geometric structure. And when you look at the geometric structure here, it turns out that you can break those into two pieces here. You can do parallel and series. And when you do parallel and series, you're going to see that you typically do some type of reduction in order to really solve these things. And you're going to see that parallel and series thinking, and I know that some of you are saying, well, yeah, we did that in 4B. I just want to tell you, you kind of did it in 4B. You're going to see that it's one of the toughest things in this course. Learning how to see series and parallel is so important. So, or you could have neither series or parallel. And when you have neither series and parallel, what you got to do here is that you got to use powerful theorems. And you'll see that one of the most powerful theorems is KVL and KCL, but we want to maximize their efficiencies. But there's other theorems like node and mesh analysis, Thevenin's theorem, Norton's theorem. There's other techniques that we want to do here. So this is what I mean by when you have the type of circuit will tell you how you're going to solve for these things. So typically what we're seeing here, I gotta find my mouse here. When I'm looking at this thing here, what we call an element is irreducible. And when I say it's irreducible, it can't be subdivided. And so typically that means that it has two terminal points. And when I think about these two terminal points, maybe I could label them A or B, or I could call them plus or minus. And what you're finding here is that when I have some type of element like this, what we're mostly interested in is we're talking about what? We want to know what the current is through this element. And we also want to know its voltage across this thing, which we typically defined as V. And the units, right? So if I talk about the units of these guys, the units only come in two flavors. You either measure milliamps, volts, and kiloohms, or you deal with amps, volts, and ohms. And you'll see that sometimes it's actually pretty hard to differentiate between them. And some books will really screw you on these units. So you want to be careful. Okay, so that being said, just go ahead and ask your question, Rico. Angel.
I wanted to ask what you meant by linear again. Did you say that was low voltage?
Well, what I want to, we should wait until a little bit later. Linear just, it's actually a fairly complicated thing. What it depends on, it actually depends on two things. It's called superposition and homogeneity, which I'll talk about a little bit later, but it's actually more involved than just saying linear. But I'll hold off until we get to there, okay?
Sounds good.
So if you guys have any questions, you can just spew it out. You can interrupt me anytime you want. Okay, here we go. Let's move on. So the next thing that we want to talk about here is we want to talk about current, voltage, and power. So here we go. So the fundamental concept of current requires some familiarity with the structure of the atom. And when we're thinking about an atom, what you find is that electrons live in shells. And of course, different atoms have different shells. So what you find here is that if I have a copper atom has 29 electrons in 4 shells. And by looking at the electron occupancy, what you're going to find here is that you get a pretty good idea why copper is such a commonly used metal in the electrical industry here. So what I'm saying here is that I have 1, 2, 3, 4. So I have 4 shells. And when you start to look at the electrons, what you're finding here is that there's 2 electrons in the first shell. There's 8 here. Maybe we should just do it like this, right? There's 8. And what we know here is that there's only 1 electron in the other shell. So that means in this shell here, there are, what is that? So 29, that's got to be 18. There's 18 electrons on the third shell. Now, of course, we're using a very simple model known as the Bohr model, but it's more complicated than this, of course. And what you're seeing here is that when you look down here, you really have the nucleus, right? So this guy's the nucleus here. And when you look at the nucleus, it turns out that the nucleus here has 29 protons. So one of the things that you find here is the question is this: why is copper a good conductor? Well, the answer is that it goes something like this here. What you see here is that if I take a Gaussian, okay, so if I take my Gaussian here, and let's say that this Gaussian, I isolate the fourth shell, right? So this is my Gaussian right here. What I find here is that if I look at the enclosed charged, okay, so if I have Q enclosed, what you're going to find here is that I'm going to have plus 29 protons, right? So these are the protons in nucleus. And if you add up all of the electrons in the shells, in the first three shells, you're going to find that there are negative 28 electrons. So the effective charge that the 29th electron sees is 1 electron charge. So all of a sudden, what you're finding here is that charge screening of the 29th electron drastically reduces the electrical attraction. And because of that, we say that this electron here is weakly bound.
So when
So
you say charge screening, that means like taking the Gaussian of it?
Well, if you just focus on the fourth shell electron, I mean, what binds the electrons in an atom? It's the nucleus. So what binds the 29th electron to the nucleus? It's the electric force. But in between the fourth shell and the nucleus are these three shells. So these three shells charge screen that 29th electron. So the effective charge that it sees is very small. It's only 1 electric charge. So as a consequence, it reduces how much electrical attraction there is between the nucleus and that 29th electron.
Oh, okay.
So that's why this is a weakly bound electron. And because it's a weakly bound electron, what we find here is that these electrons I should say at room temperature can easily move between one copper atom and another. And because of this, copper is a good conductor, right? So then this makes copper a good conductor. I mean, you already knew that copper was a good conductor, but it's that weakly bound electron. I mean, the two most common elements that people use in electronics is typically copper or gold. But the best conductor, without any doubt, is aluminum. if you look at its resistivity or its conductivity, its resistivity is the lowest. But the problem with aluminum is that it has issues of thermal expansion, stuff like that. But if you look at power grids and stuff like that, power grids use aluminum because copper's too heavy. So they have to worry about temperature and stuff like that.
Is that what? So that's what high tension. What are high tension wires made of, or where do they use the aluminum?
They use them to in the transmission lines. Because if you were to look at copper, like, I mean, its density is much, much higher than that of aluminum. But if you can control the heating, then aluminum is an ideal, conductor to use in this situation. But there is very, very, very little current that actually runs through those transmission lines. And you guys, I'm pretty sure you probably talked about that in 4B. So what I want to do here, and in fact, if I remember correctly, I think they even use aluminum, even in airplanes, just because the density is so much higher. If you get a chance, you should read about what's it called? The space shuttle. When the space shuttle went fiber optic, you should see the amount of weight that it lost because goddamn copper wires were so damn heavy. Something to look at that. That's a Google thing that you should look at. Okay, so now that we sort of like established that very briefly here, what I want to do here is that I want to go in and I want to start looking at what do we mean by the units and sort of like the sign conventions that we're talking about. Okay, where's my mouse at? Here we go. So what you find here is that suppose we have a short piece of copper wire. So what you find here is that if there is no E field or voltage across it, then the electrons drift, right? They have a drift velocity. And this drift velocity implies that you have random motion. Now, this random motion is really due to thermal agitation of the electrons. Like if you take, one question that you can ask yourself here is this: can you heat up a wire, right? Let's say you take out your Bic lighter and you have a piece of copper wire and you put that Bic under the wire and heat it while you're transferring energy to the electrons. Are you going to get a current flow for that wire? The answer is no, because it's a random motion. And so when you look at this over time, that random motion essentially brings it back to its original position. So there's no net current flow. The only way you can get a current flow for a wire is if you put an E field, but we don't want to use the word E field because that's arcane. We want to talk about an electric potential, a voltage across the wire. So what we say then, that if a voltage is across the wire, now electrons flow in one net direction. And what we find here is that there's two kinds of flow, as we could say this. And what we find here is that there are two kinds of electron motion. The first one is the electronic flow. The second one, I know people call it the flow of positive charge. It's actually not the flow of positive charge. It's called whole flow. But people will then come in, it's really whole flow, and whole flow is the same as positive charge flow. Now, whole flow or positive charge flow is called the what do they call it? I forgot what they call it. It's like the conventional flow of, that's what they call it. It's called the conventional flow of current. And that's exactly what we do in this course. And to be honest, that's exactly what you use all the time, right? If you're going to tell me that you really think in electron flow, I'm going to call you and say you're BSing me, because let me ask you this: when you look at your battery, your car battery, there's a red terminal and there's a black terminal. Which one's the high terminal? I'm assuming you're going to say the red. There you go. You're already talking about conventional flow. So we don't have to worry about electronic flow. But it really doesn't matter mathematically. It turns out that the equations, you can actually do them with electron flow or positive flow. And if you do it with electron flow, what you do here is that you carry a minus sign the whole time. But on both sides of the equation, it's going to be a minus sign, and they cancel out anyways. So it really does not matter. And so the true definition of current then, right? So if I now write down a definition, what we say here is that current is then going to be what? It's the number of positive charges, right? Positive charges per time interval. That's what we mean by current here. And so typically, I'll write this as a, as in terms of a differential, but it doesn't have to be this way, right? If we're talking about linear elements, then there is no differential. But if we want to make it in general, where we include capacitors and inductors, it should be a derivative. So then our definition of current is typically time, I, little I, and this should be, and then Q is the standard. So then this becomes our definition of current here. And so when I look at this thing here, what you're seeing here is that you're really seeing the following thing here. What you're going to find here is that if I look at this guy, so when I talk about a unit of measurement, even though we kind of talked about it briefly, we should just say it really. One thing, the following way here is that a unit of current is really, by definition, 1 coulomb per 1 second. But if you look at this, 1 coulomb is about 10 to the 25 electrons, right? Or electron charges per 1 second. And this, by definition, is what we call 1 amp. Which of course we don't write it this way, we write it that way with A. So if you have 10 to the 25 electrons that have some drift velocity and moving with uniform velocity, then we know that that's about an amp. So let's look at our sign conventions. Okay, so what do I mean by a sign convention? Well, our sign convention for current direction, since we've already talked about this already, is that if I have a piece of wire and current is moving in this direction, the only way this could be possible is that this here is the high potential and this end here is the low potential. So that means in this sign convention, I would literally come in here. So my sign here tells me that this would be plus I. That's our sign convention. On the other hand, if I have a wire that does this instead, and I still have my sign convention for the potential here like this, if I have a current that flows upstream, and I define that as the current here, you want to be really careful here. This sign convention then includes a minus sign. So that's the sign convention that we want to really look at here. We want to be careful about these guys. Now, to sort of like set you up for one of the examples that we're going to do here, what you're going to find here is that current can vary as a function of time, and therefore I can rewrite this expression here. So we can rewrite the current equation as, that is, if I write it like this, oops, sorry about that, then clearly I can solve this equation by sort of like integrating this guy. So one way that I can get the total amount of charge here is sort of like integrating that equation to get that. And depending on the current will tell us, you know, effectively what type of source is in the game here. So I can give you just a couple examples to actually tell you what I mean by this. So how much charge is acquired by an element must depend on the type of source. So for example, if I look at the first case that I'll look at is I'll look at a constant source. So if I look at a constant source, then that means here that my voltage source should be a constant. So for example, let's say I have a source that's 10 volts. So if I have a source that's 10 volts and that voltage source doesn't change, then we expect a constant current value, whatever that source is here. So picture-wise, what we mean by that is that if I have a constant current source, right? In this case, let's call this, let's say that this is I of t, and I'm going to call this guy big I, where big I is a constant. So if I look at this guy here, you could see that this guy right here is essentially going to be what? This is going to be an area. And this area here then represents the total charge acquired between some time 0 and some time t here, right? That's what that quantity should tell us here. Another, simple case that we could think about this, we can also think about an AC source. What happens if I have an AC source? Now, an AC source one example could be that it looks something like this, which is sinusoidal. Since the source is sinusoidal, then the current should be sinusoidal. So we expect here an AC current value. In other words, if I look and I plot, since the source is AC, then I expect that the current should be AC. And let's just look at just one cycle here. So in this case here, you're seeing that I of t here should be something that should look something like this here. So if you look at how much charge was acquired by the element during this brief moment of time here, you can see here is that there's a positive pulse, and now there's a negative pulse. So when you're looking at the area of this thing here, so if I look at Q total, and I'm looking at the total area, this area must be 0. So if I have an AC source, like your outlet in your home, and you ask, how many electrons did that AC source actually put into your house? The answer is, of course, 0. It got 0 because charges don't have net motion in AC sources here. So there's lots of ways to look at this thing here, but that's one example of how you would look at the charge and the current here. Okay, so now what I want to do here is that I want to go in and I want to move onto voltage here. And I think here's where voltage is going to be, I'm fairly confident that the way Marcus talks about voltage and the way I talk about voltage are quite different. So let's get to it. Voltage, right? So when I talk about the word voltage, voltage has a very specific meaning. The true thing about voltage is really what? It's the potential. Voltage is the potential difference. And there's many kinds, there's many ways to get a voltage here, right? One of the questions I typically ask my 4B students is I ask them this: tell me the difference between these. Tell me the difference between electric potential, voltage, EMF, back EMF, right? And induced EMF. And the crazy thing is they all have the same units. And each of those statements are actually different from each other. How you create these different quantities is it depends on the physics of what is going on right here. And what we find here is that the vast majority of the time when we think about potential, we talk about constant potentials. Even though most of the potentials that you deal with in 4B are not constant, they're variable because you're talking about point charges or spheres or planes or whatever it is that you're talking about. But in power supplies, you typically have a constant voltage. Now, I got to be careful about what I'm going to be saying here, but ultimately what we say here is that we start off with something called electric potential. And the electric potential is a topographical parameter. And what I mean by topographical parameter, it's really what I call the electrical landscape set up by the source charges. So what I mean by that is that when I have a source charge, it actually creates a space in this electrical space. It creates mountains, it creates valleys, it creates hills and stuff like that. So when I talk about a difference in potential, that by definition is voltage. So you never say a voltage difference. That's redundant. Potential difference is the definition of voltage. And if you look at voltage, this is the electrical height of a charge in this electrical space. And what you find here is that voltage is different than potential energy. And what you're going to find then is that electrical potential energy is really the work done by an electric force, right? An E force. So I'm just putting down some very, very, very basic definitions. But my goal here is really to say the following thing here, is that in order to move a charge from A to B, work must be done. From A to B, work must be done. And the only reason why we even care about, potential is because we can use conservation of energy. And problems using conservation of energy are considerably easier than problems using electric forces or forces in general. Forces require differential equations. Energy involves linear equations. So if you can calculate the potential, then you can get the electrical potential energy. And now you can use conservation of energy, which we all agree is much easier to use. So we have to talk about the work here. So the most common picture that people paint about voltage here is that we look at constant E field. We want to look at a constant E field. And the only way you can get a constant E field is if you have parallel plates. So if I have really, really big parallel plates, right? So if these are my parallel plates right here, and I have, let's say this is my positive and this is my negative plate, we could say here is that I'm going to call this plate A and this plate B here. So essentially what I'm doing here is that I'm going to place a charge, a positive charge in this field. And what you're going to see here is that because of this, there's this electric field. And this electric field is going to apply what? It's going to apply some electric force on this charge, and this charge is going to move a distance. And what we know here is that this work, right? The work is really going to be the electric force times some distance that you integrate this field across. That's what we mean by work. So what does the electric field of these parallel plates do? They do work. They move a charge from, let's say, the upper plate to the lower plate. But it turns out this is the worst possible way to actually view charges. We never, ever, ever want to look at electric fields. Sometimes we will look at electric fields just because it might be easier to conceptualize it. But 99% of the time in this course, we don't give a damn about electric fields. Circuits is about voltages, period. Let me ask you this. When you wired things in Physics 4B, did you ever go try to calculate the electric field? What did you attach? A multimeter. What did you measure with the multimeter? A voltage. We don't give a damn about electric fields in circuits. We only care about voltages. Now, what's special about this is that this is a constant D field. And because this is a constant D field, it turns out that the potential function is a linear function. So what you find here is that this is, so now if I write this in terms of the potential field picture, it looks something like this. What you find here is that this guy here represents a positive plate, and this positive plate, we already know, has some value here. But wait a minute, what do we measure this from? We measure this from the potential difference here. And what you're going to find here is that we have a second plate. And when you look at that second plate, the lowest part of the plate is typically called ground. The negative plate is typically called the ground potential. Could I use any other words? I could have called it the potential of B. So in this case, we typically call it the ground. So this is typically the ground, which means the lowest reference potential. And in this course, you're going to see that the ground we typically write like this, which is what you typically see in circuit diagrams. So the question is, what does the potential function look like? The potential function itself is actually a linear line. It's a ramp. So what did these parallel plates do? They created a ramp. And what you're finding here is that this guy is an energy field. Charges cannot penetrate this energy field. So that's the potential right there. So when I say a potential difference, and I said that it's a voltage, and that voltage is the electrical height, what do I mean by voltage? What I mean by voltage here is that the height difference from here to there is what we call voltage. Okay? So that is voltage right there.
Carlos, what do you mean when you say charges can't penetrate that?
I mean, there's an energy field that charges cannot go through that. When I look at, let me ask you a different question. So here's an analogy. Let's say you're riding your bike down the mountain. And to give you an example of this, you have a constant gravitational field on Earth, right? So if I look at the Earth's gravitational field, that guy's a constant. You know what's interesting about this? Look at that G. look at that E up here. E up here is what? Constant. So it turns out that the gravitational potential, not potential energy, gravitational potential is also linear. But my analogy is this. Imagine that you're riding down a hill on your bike, right? You're on your bike and you're riding down a hill. Why don't you go into the ground? Right?
Normal force.
The same reason, if you put a charge on that potential field, it can't penetrate that field. And so what you're finding here is that now that you know what, I'm going to move this because Isaac screwed me up in how I wanted to place things. So you can blame him for it. So what I'm going to do here is I'm going to move this over here. So now what I want to do is I want to go highlight this guy and I'm going to copy this guy. So here we go. So now check this out. What we want to do is we want to do this now. We want to say, what is work done? Right? So now if we want to talk about the work, here's what we got to do here. It turns that in order to do work, you need two things. You need something to apply the work to an object. So now I'm going to come over here and I'm going to place a positive charge. But wait a minute. Why do we want to talk about potential? Because potential, which is the most hideous goddamn name you could possibly give something to, why the hell would they call it a potential? Because everybody who says the word potential thinks what? Potential energy. Unfortunately, it's not even close to the same thing. But check it out. I now have what? Electrical potential energy. This charge has potential energy now. And that potential energy here is what? Is connected to what? The work done by the field. And when this charge gets all the way down to the bottom, what do we know about the charge at the bottom? It converts all of its charge into what? Kinetic energy. That's why we deal with potential. Because conservation of energy is much easier to deal with than electric fields. And so what you do with your multimeter is that you effectively are going to calculate the potential energy of that charge at that location relative to ground. So when you go with your multimeter, your digital multimeter measures electrical heights. And essentially, this is proportional to the electrical potential energy of the charge. So now that we kind of established this, now we could sort of like write down in detail what we mean by, what do I mean by work here? So it turns out then, so we can connect the work. So work and potential energy are related. And the way they're related here is that we say that the work is actually Q minus the change in the voltage here. So typically, we don't really think about voltage here as work per unit charge, but it's of some use a little bit here. So when I talk about the electrical height or the voltage here, picture-wise, what I just showed you up here is exactly what we mean by this. So that's the definition of voltage. And I know that that's all pretty conceptual, but I figured we should write down voltage properly for the first, before we move on here. Okay, here we go. So now what we want to do here is that I want to go in and I want to talk about power now. So when I think about power, this is another one that it's going to be, well, we'll see what happens. So let's talk about power. So we want to talk about power.
Wait, Carlos, there's a question that was like asked in the chat, and I have it too.
What is it?
For the picture of the voltage with the ramp, does it matter like whether that ramp goes like to the top of the bottom plate or to the bottom of the bottom plate?
It does. Right? Let's think about this thing here. When you think about your car battery, which one's the high?
The battery is the low.
Yeah, but which, so you have a red terminal and you got a black terminal.
Mm-hmm. Okay, the red is the high.
So in other words, that's the 12 volts.
Mm-hmm.
When I look at the black one, that's what we call ground, which is attached to the chassis of the car. That's what we call 0 volts. So which direction is charge going to go? If I'm talking about positive charge flow, it's going to go from the red to the black. So the analogy is here, if that's the case here, then this charge has to slide down this electrical ramp because it's going from the high potential to the low potential. And you'll see, here's where I'll start talking about passive versus active elements. Okay. Was that the question? Oh, let me see. What did I do?
I think that answers it. If
Okay.
the ramp goes like down to the bottom of the plate, it would stop at the plate instead of rolling onto the plate, right?
Yeah, but this is a fake situation. And the reason why is that this isn't a power supply. A battery is a power supply. And when we say the word power supply, what we really mean here is that there is a flow that batteries, everybody says, oh, they put out voltage. No, they put out voltage and current. And power is voltage and current. These parallel plates do not put out, they put out a voltage, but they don't put out a current. So it's not a source. A battery is a source. And we'll get to that right now, as you'll see.
Okay, for sure.
Okay, what's this? The other question. So Josh asked the normal force, laugh out loud. The normal force is the magnetic force, right? The Paul exclusion principle. So I'm going to ignore Josh. Let's move on.
Yeah, that's probably the best thing to do.
Okay. Josh, you already know me, right? I'll go right at you, unfortunately. Okay, let's move. Let's talk about power. We want to talk about power dissipated / delivered. And this one might blow your mind a little bit, okay? And it's because you have some misconceptions left over from physics 4B. By the way, it's normal, okay? It's not nothing that Marcus did. It's just that people just kind of don't believe it for a while. Okay, so here we go. So the other parameter that we said is important is we said power. So a power function is actually the current times the voltage. So power is the work done per unit time. In other words, when I look at our definition of power, it's actually work per time. But now let's put it into differential form. If we put it into differential form, It's really the work per unit time here. But wait a minute, I can use the chain rule here. And if I use the chain rule, I can write the work as a function of charge in this way here. But if you look at this thing, look at this guy right here. That guy is the voltage. And this guy over here is the current. In other words, this tells us here that I can write this guy, the power, as the voltage times the current. And so in a circuit, it's easy to measure the voltage and the current with the meter, and that's the power of this thing here. To get the energy, we have to integrate this thing here now. So if you look at this thing, we see that the work is also, right, from the work energy theorem, energy and work are the same. Remember, this is energy and not the electric field. And this guy here is then going to be equal to the voltage times the current here, right? And this is what power is. So you could see here, so if we want to get the energy or the work, so it's common in circuits not to write E for energy, but to write work. Work and energy are the same, effectively, according to the work energy theorem. So then this has to be the integral of these guys right here. And so from some element, some time interval to here, this is the energy here. Now, when I think about this guy here, you could see the advantage of the power versus energy here. So if you want to think about this mathematically, what do we want to do here? So power is much more useful than energy for two reasons. One, you could look at it mathematically, right? Oh, how am I spelling mathematically here? So when I look at this mathematically here, I mean, it's easier not to integrate. Look at that. You'd have to integrate this thing in order to get the energy. That's crazy. But if I want the power, I just multiply the voltage times the current and I'm done. But the most important thing here is measuring energy is difficult. In fact, it's really difficult. And the reason why here is that you have to isolate the component or element and worry about the heat emitted by the element. About the heat emitted into the environment. Oops, there's an N right there. Into the environment. And you got to admit that that's pretty hard. So if you're heating up a resistor, for example, or a capacitor or an inductor, you are generating heat. And as a consequence, what you're going to find here is that you would have to capture that heat to find out, what conservation of energy is. But if you look at power, you don't have to do that. All you got to do is you just got to measure the voltage and the current with the meter, and you got it. So energy is not useful. So, but conservation of energy and power are really proportional to each other. So, but we like the idea of energy. Why? Because conservation of energy. Why do we like the idea of conservation of energy? Let me just scroll up again. Look at this picture. Conservation of energy allows us to physically understand what's going on in the system. So since energy is proportional to this, then we can also say that this is proportional to conservation of power here. So we really want to look at conservation of power in a system. So now let's get to what we really want to get to here. What we want to do here is that we want to talk about power dissipation and power delivery. So let's talk about power dissipation. So you could see me say energy dissipation, but no, that's not what I said. I said power dissipation. So power dissipation by a resistive element can be either good or bad. But what you're finding here is that what we mean by power dissipation is that, let me give you an example. Suppose you have a toaster, and in this toaster, you're throwing in a bagel. So the power dissipated by the resistive element of the toaster is a good thing, because what does it do? It gives off heat. And that heat is good because it makes the bagel taste better, it being toasted here. So what you're finding here is that when I talk about power dissipation by resistive element, what we're finding here is that the resistive element, what it does here is it absorbs energy from the circuit, right? It absorbs energy from the circuit. And what I mean by the circuit is that I really mean the power supply. So in this case here, if you're plugging it into PG&E, then you're using the outlet power supply in order to do that here. When it absorbs energy, we then say that the element is a passive element. Okay? The element is a passive element and absorbs power. On the other hand, you can have energy that's not passive, but is delivering energy to the system. As an example here, you can have power delivery.
Carlos, I'm a little confused by the box part. Do you mean to add resistive element is a passive element, or?
No, just a passive element.
Okay.
I mean, I gave you an examples of a resistive element, but it doesn't have to be resistive. Like one example, is a capacitor passive? Does it absorb energy from the circuit?
It does observe.
Okay, so what if I charge a capacitor and I take it out of the circuit? And now I connect it to a light bulb. Is that capacitor passive?
It should be passive because there's no voltage, right? Or
No, it has a voltage. It has a voltage.
It does have the voltage. Never mind.
Yeah,
yeah.
and here, let me talk about active, and then you'll see, then we can come back to that question, because I think it's an important question and one that I think is going to cause some trouble for some of you. So power delivery, power delivery occurs let's say during a jump start. So imagine that you hook up two batteries. One's a bad battery, one's a good battery. The good battery is delivering power to the other battery. We got to be really careful how we talk about that power. But that's an example of that thing here. And what you find here is that the supplying battery, so then what we say here is that supplying battery, what does it do? It delivers energy to the bad battery. So what we say here is active element deliver power. Active elements deliver power. And that's the two classes of elements that we have here. So what we need to do here is that we need to go in and we need to start talking about the following thing here. And it goes something like this. Okay? So let's talk about passive elements. So what do I know about a passive element? So what we say here is passive elements is when electric charges that are moving across this element lose electrical potential energy. So passive elements lose potential energy as their charges when their charges go across them.
So it's the way you say it is that the element loses potential energy,
Yep.
or not the system.
Nope, the element. But by the way, it's part of the system, right? But we're really only talking about the element per se, because you can have 30 elements in a circuit. So all of the energy must be coming from the supplying batteries or power supplies. And there's things, and well, we'll have to, I'm getting ahead of myself. So what do I really mean by this? So picture-wise, I really mean this here. And what we did here is that we talked about this guy right here. Right? We said that this is the positive, this is the negative. And so when you're looking at this guy here, what you're finding here is that I have a charge, and this charge is literally decreasing electrical potential energy, right? It's going from a high to a low, and that guy definitely loses potential energy as it goes down this hill. But element-wise, right, the element picture looks like what? So if I have an element, it looks like this. So that means if this is the positive terminal, and this is the negative terminal, which is the direction of the motion of the charge? It's going from the positive to the negative. So anytime charge goes from the positive terminal to the negative terminal, the element is passive. You know what? I got to stop.